looks like a cake sliced into squares and rectangles.
To me, it looks like a woman's bandana or a man's handkerchief.
I see 3 squares and 6 rectangles of different sizes.
3 squares? Don't forget the biggest square that surrounds the whole figure.
Actually, you're all correct. Paintings show geometric shapes, which are also algebraic expressions.
Algebraic expressions? I don't see any numbers.
Nor letters. How can that be?
You'll know soon enough. That's our lesson for today. We all have names. It's how people know us, call us, and remember us. In algebra, there are names by which we understand mathematics better. For example, it's so much easier to understand the language of algebra than long words, sentences, and paragraphs. Algebra works with symbols, numerals, and letters, which stand for quantities which in turn form meaningful expressions. Algebra is sometimes referred to as a shorthand way of writing ideas. One of the simplest and most common expression is a polynomial. Can you think of words that start with the prefix poly?
Polysyllabic. Polysyllabic.
Polygon.
Polyglot.
The meaning of poly is several or many. Other prefixes which you come across in everyday language also includes mono, bi, and tri.
Saluhin mo ba ako yung pag nahimatay ako? Hindi. Anong gagawin ko pag nakita ko siya pag pinakilala niya?
Monologue.
Tatakbo ba ako?
Bigamy. Triangle. Tripod.
Monotheism.
Bicycle.
Can you infer what mono means?
Yes, it means 1.
And the prefix bi implies 2.
Very good.
Then tri would mean 3, as in the tricycle I ride in every day has 3 wheels.
If monomial in algebra means one term, what does binomial mean?
2 terms.
And what do you think trinomial suggests?
3 terms.
Very good. Polynomial suggests many terms. However, to simplify things, the term polynomial could refer to algebraic expressions with 1 or more terms. When one wishes to stress the number of terms, we use monomial to refer to an expression containing 1 term, binomial for 2 terms, and trinomial for 3 terms. Beyond 3 terms, in fact, using 1 or more terms, it is mathematically correct to use the general term polynomials.
Excuse me, sir,
Yes.
but what's a term?
A term is a number or an indicated product of a number and a variable. Polynomial terms are separated by a plus and minus sign. These signs indicate addition and subtraction. For example, 3x squared is a term. It is the indicated product of 3 multiplied by x squared. X squared is the indicated product of x multiplied by itself. X times x equals x squared. In 3x squared, we call 3 a numerical coefficient. X is a base and a literal coefficient, and 2 is the exponent of x. The exponent tells how many times the base is multiplied by itself. In the term 4x cubed y, 4 is called the numerical coefficient of the term. X is one of the 2 literal coefficients. Y is the other literal coefficient. 3 is the exponent of the literal coefficient x. 1 is the exponent of y. An exponent of 1 is usually not written. When not written, it is understood to be 1. A polynomial in x is an expression of the form a sub n x raised to the n plus a sub n minus 1 x raised to the n minus 1 and so on, plus a sub 2 x squared plus a sub 1 x plus a sub 0, where a sub n is not equal to 0. Note, however, that a's are real numbers and n is a non-negative integer. Let me give you some examples of polynomials. Can you tell me how many terms these polynomials contain? 2x plus 5. Carla?
2 terms, a binomial.
That's correct. But next time, try to be sure of your answer. What about 3x squared plus 7x minus 5?
3 terms, a trinomial.
Very good. 5x cubed minus 7x squared plus 2x plus 4.
4 terms, simply called a polynomial.
And what are the coefficients of the last polynomial, Mia?
The polynomial 5x cubed minus 7x squared plus 2x plus 4 has coefficients 5, negative 7, and 2.
I noticed that the polynomial is written with descending powers of x.
Good observation. That is called the standard form of the polynomial. In a polynomial, the term which does not contain the variable, which in our definition is a sub 0, is a constant term. Note that in the definition, all exponents should be integers. For polynomials in more than one variable, the degree of a term is the sum of the powers, or exponents, of the variables in the term. The degree of the polynomial is the highest degree of all its terms. 5x squared is of degree 2. 5xy is of degree 2. 5y cubed is of degree 3. 4x squared y cubed is of degree 5. The polynomial 6x cubed y plus 3xy squared is of degree 4, which is the degree of 6x cubed y, the term with the highest degree. To be in standard form, the polynomial should be written with descending powers of x. This way, the degree of the polynomial is easily seen. Examples. The coefficient of the term with the highest degree is called the leading coefficient. So we can simplify the definition of a polynomial as a sum of terms, each of which is a product of constants and variables raised to whole number powers. In a polynomial, a variable cannot appear in a denominator as an exponent, within a radical, or within absolute value bars. Now, which of these are not polynomials?
Number 4 is not a polynomial because the variable x has a negative power.
Okay.
Then number 7 isn't a polynomial either because the variable x has a negative power.
Number 5 is not a polynomial because it is with a radical.
Number 8 isn't a polynomial because the variable is under the division sign.
You're correct in saying that number 8 is not a polynomial, but don't confuse the fraction bar as the division sign. When the variable is in the denominator, the number is not a polynomial.
Number 9 is not a polynomial because the variable x is an exponent.
Number 10 isn't a polynomial either because the variable x is within absolute value bars.
We can add or subtract polynomials in much the same way that we add or subtract real numbers. We simply add or subtract like or similar terms. Like or similar terms are terms with the same variables raised to the same powers. Here are some examples for addition. To add horizontally, we group together like terms. When adding vertically, we place like terms in the same column. Do you recall the rule for adding numbers algebraically?
Yes, if the two numbers have like signs, we get the sum of their absolute values and affix the common sign.
And what if they have unlike signs?
We subtract their absolute values and affix the sign of the greater absolute value to the difference.
Good. How about the rule for subtraction of signed numbers?
Easy. We change the sign of the number to be subtracted, that is the subtrahend, and proceed as in algebraic addition.
Here are some examples of subtraction of polynomials. What property of multiplication is evident here, Carla?
Commutative property?
Nope. What do you think, Bea?
Distributive property, like redistributing the operation to the terms of the binomial.
But do we also do that when we multiply terms vertically, Mia?
Yes, we do.
How about when we have more than one term in the multiplier?
Yes. How?
Well, we multiply by one term at a time, then add the partial products. Done horizontally, we get the same results. There's a shorter and faster way to do this. Do you recall the FOIL method? FOIL is the acronym for getting the product of two binomials horizontally. F stands for the product of the first terms. O stands for the product of the outer terms. I stands for the product of the inner terms. L stands for the product of the last terms. Now see if you can get this product orally using the FOIL method.
The product is 6x squared plus 11x plus 3.
Okay, what happens when the two binomials to be multiplied are the same? For example, quantity 2x plus 3 multiplied by quantity 2x plus 3. This is equivalent to squaring the binomial quantity 2x plus 3. And if we apply the FOIL method, we notice something special. The resulting trinomial has special characteristics. These are: number 1, the first and third terms of the trinomial are perfect squares. They are the squares of two terms of the binomial being squared. Number 2, the middle term is twice the product of the first and second terms of the binomial. Thus, to square a binomial, we simply A. Square the first term, B. Double the product of the first and second terms, then C. Square the second term. Try it on this one. Use these aids. This means square the term. This means multiply and double. The result is a perfect trinomial square. Can you do this fast without using pencil and paper?
100x squared plus 140x plus 49.
16x squared minus 24x plus 9.
Do you notice another special characteristic of the square of a binomial? That is, about the signs of the resulting trinomial square?
The first and third terms of the trinomial are always positive.
That's good. Notice too that the sign of the middle term follows the sign between the terms of the binomial being squared. Now here's an application of the square of a binomial. What is the area of a square whose side is quantity 3y plus 4?
Area equals side times side.
Good. A is equal to quantity 3y plus 4 times quantity 3y plus 4 is equal to quantity 3y plus 4 squared and is equal to 9y squared plus 24y plus 16. From the diagram, we see the smaller square whose side is 3y. Its area 3y times 3y is equal to 9y squared. The area of the smallest square is 4 times 4 equals 16. The area of each rectangle is 4 times 3y equals 12y. Since there are two such rectangles, their combined area is 24y. Thus, the area of the large square, whose side is 3y plus 4, is quantity 3y plus 4 squared equal to 9y squared plus 24y plus 16. Now, how can we use this in mental arithmetic? Suppose we want to get 31 squared mentally. We can think of 31 as quantity 30 plus 1. Verify your answers on a calculator. Are you convinced that it works?
Yes.
But you can still do the squaring faster. Start from the rightmost digit. 4 squared equals 16. We write 6 and carry 1. Quantity 4 times 2 doubled equals 16, plus the 1 carried equals 17. Write down 7, carry 1. 2 times 2 equals 4, plus the 1 we carried over equals 5. Therefore, 24 squared equals 576. Can you do this mentally? Now try it with bigger numbers. Because algebra is a language, do you see how knowledge of algebra makes things easy?
Yes. I never thought I could solve more difficult equations mentally.
Okay, you all did well. We've covered a lot.
Yes, we did. We studied algebraic expressions and defined a polynomial in X.
We also wrote polynomials in standard form and practiced operating on polynomials.
We also squared numbers mentally.